Okay. So assume there is a uniform rod of length L and mass M placed along the x-axis as you see here. One end of the rod is at x is equal to 0. The other end obviously will be at x is equal to L. Okay. One of you quickly tell me how many different particles will be there in this rod?
Infinite.
Infinite number. Okay. We have to find out the position of center of mass of all these infinite particles, of the system consisting infinite particles. And as you can see, there's no gap from particle to particle. So we call this as a continuous mass distribution. All the objects that we come across in daily life are continuous mass distributions. Okay, so we are starting with a simple case, that is this rod. Now, one of you tell me, what is the basic formula for position of center of mass? RCM is equal to?
Sir, M1 R1 plus M2 R2 plus
Okay.
whatever and then by M.
Sigma mi Ri divided by the total mass of the system, which is sigma mi, summation of masses of all the particles. Okay. Now, if there are a finite number of particles, then we can multiply each mass with its position and substitute here and get the answer. But if there are infinite number of particles, we can't substitute each mass multiplied with its position and add them up. Okay. So what we are going to do is we will convert this into a form which can be applied to a continuous mass distribution. Now, this formula is applicable when you have a collection of particles. Okay, a finite collection of particles. Now, mi here is nothing but the mass of the ith particle. Okay, it could be the first particle, second particle, 10th particle. So we call it as the mass of the ith particle. And Ri here is the position of the ith particle. Okay. Now, if you are given a continuous mass distribution like this, what you have to do is you have to visualize it as a collection of particles. Okay. So we'll consider a small part of this rod, maybe from here to here. Okay, it should be like a particle. It should be so small that it's actually a particle. But for us to be able to visualize, I'm showing significant width. Let's say its width is dx. Okay, small width along the x-axis, so I can call it as dx, not an issue. So this is the small particle that we have considered. We call it as element. We don't call it particle. We call it element. Okay. And for that element, there is a particular position vector. This one. Let's call the position vector as r. If it's along the x-axis, you can simply call it as x, not an issue. And assume the mass here is dm, mass of that element. Okay. So that mass has that position vector. You can consider another element also. You can consider as many elements as you want. Take another element somewhere here. This is also a small mass like a particle. Let its mass be dm and it will have its own position vector. You can call it as dm2 and its position vector as r2. For the first one, you can take position vector r1 and the mass as dm1. Okay, like that, the rod is a collection of many particles, infinite number of particles. Now see, what you have to do to get the position of center of mass is that you have to add up all these. Sigma mi ri means m1 into r1 plus m2 into r2 and so on. So in this case, what you'll do in case of a continuous mass distribution, what you'll do is first mass is dm1, first position vector is r1 plus second mass is dm2, that second mass's position vector is r2, and so on. There will be infinite terms now. It's not up to n terms. Okay, there are up to infinite terms now. And you have to divide that by the summation of all the masses. Mass of the first element plus mass of the second element, so on. Here also there will be infinite terms. Okay. Can one of you tell me the meaning of dm? What does dm mean?
Mass of that elemental parts.
Mass of the small element that we have taken. How much could it be? Like, will you be able to specify its mass?
No, sir.
No. See, we know dx means a small change in x. So small it tends to 0. You can't tell how much it is. It's not 0, but it tends to 0. dy is a very small change in y. Similarly, dm is a very small mass of this system. How small it is, we cannot tell. It will be tending to 0. Now, if dm tends to 0, then dm multiplied with r will also be tending to 0. This is a very small term. Or properly expressed, or if you call it properly, it should be called infinitesimal. Okay, these are very, very small terms whose values you cannot even specify. And there are infinite number of such small, small terms. Okay, and you have to add them. How do we add small, small terms whose value is not even known? We integrate them. Okay, therefore, for a continuous mass distribution, the position of center of mass is calculated like this. Summation becomes integration. For a finite number of terms whose values you know, you can use the sigma symbol, summation. But there are infinite number of terms, and each term is so small we don't even know how much it is. Okay, so we do integral, and what should we integrate? R dm. Okay, position vector multiplied with the small mass, and you have to integrate that over the entire system and divide by what's in the denominator, the summation of the small masses, integral dm. So this is the formula for position of center of mass of a continuous mass distribution. Sigma changes to integral. Mi, mass of the ith particle, changes to dm, mass of a small element. And Ri, position of the ith particle, changes to r, position of this dm. Okay. Therefore, if you only want x coordinate of the center of mass of a continuous mass distribution, this is what you need to do. Integral x dm divided by integral dm. Similarly, if you only want the y coordinate of center of mass, you do integral y dm divided by integral dm. Similarly, the z coordinate also. Okay, so did you all understand how the summation formula changes to the integral formula? Summation is to be used when there are a finite number of particles, and that too, you know how much each term is. You should know the mass of each particle and the position of each particle. Then you can use the sigma symbol. But if there are infinite number of terms and each term is so small you can't even express it, then you convert it to an integral. So mi changes to dm, ri changes to r. That's all. And sigma changes to integral. Okay. Now, the given system here, the rod of length L placed along the x-axis, it's a continuous mass distribution. Okay, I want you all to note down these formulas, x coordinate of center of mass and y coordinate of center of mass for continuous mass distributions. We'll be using this. Okay. So what we need to do is, we need to consider a random element of the system. Let's consider that blue one. Assume its mass is dm, its position is r, or since it's along the x-axis, let's just call its x coordinate as x itself. And because the element is along the x-axis, you can call the length of the element as dx, because dx has a meaning. dx is a change in x, or change in x coordinate, you can say. So that small length has to be along the x-axis, only then you can call it dx. If the length is in some other direction, you can't call it dx. Okay. Now we know that if all particles lie on the x-axis itself, then the center of mass will also be on the x-axis. Okay. So if you want the x-coordinate of center of mass, you need to do integral x dm divided by integral dm. Okay, one of you tell me, what is integral x dm? Okay, there's no direct answer for it. What is integral x dx?
X square by 2.
X square by 2. Generally, integral of x power n dx is x power n plus 1 divided by n plus 1. If it's only x, it means x power 1. So it becomes x power 1 plus 1 divided by 1 plus 1, x square by 2. But to find the center of mass position, you need to integrate x dm, not x dx. Then what to do? Any idea? There's no way you can integrate this directly. You can't put x outside also, because from element to element, the x value will change. X is a variable. You can't put it outside. If you want to integrate this, you need to make some changes. See, x is the variable, right? And you are trying to integrate with respect to mass. That is why this cannot be done. So what you need to do here is convert dm, or not convert, I should say, express dm in terms of dx. Then you will be able to integrate it. Okay, the variable, and I mean the variable in which the function is written, the function here is x, and the variable with respect to which you are trying to integrate should be the same. Here the function is in terms of x, but you are trying to integrate with respect to mass. Cannot be done. So you have to convert it to a single variable first. So you can express dm in terms of dx. There is another thing also you can do. You can change x to m terms. You can convert x to m. Okay, but that will be difficult to do in this case. We'll not do that. But there are some situations where that also can be done. So you have to express dm in terms of dx. One of you tell me, what is dm in all this? What is the meaning of dm?
Mass of dx, sir.
Mass of the small element that we have considered. Okay, dm is the mass of the element, and dx is the length of the element. Okay, see, some of you may say, sir, the element has some thickness also. No, we are considering a rod, and as far as your syllabus is concerned, a rod is just a straight collection of particles. It doesn't have any thickness. If it has thickness, it becomes a cylinder. Okay, it's a very, very thin wire which cannot be bent. You call it a rod. Okay, just for us to be able to visualize, I have shown significant thickness. Okay? But you have to ignore the thickness of a rod. Okay, it's very small. Fine. So dm is the mass of the element, and dx is the length of the element. Now we have to express the mass in terms of the length. Okay. Saket, you tell me, suppose the total mass of the rod is m over a length L. How much will be the mass for a length L by 3? If m is the mass for a length L, how much will be the mass for a length L by 3?
M by 3, sir.
M by 3, 1/3 of the mass. Okay. This is where this term becomes significant. uniform rod. Uniform means it has the same distribution everywhere. Means the particles are all similar. You don't have heavy particles on one side and light particles on the other side. All particles have same mass. Okay, so all the particles are similar to each other. Only then you can say 1/3 of the length will have 1/3 of the mass. Half the length will have half the mass. Fine. So it is important to note whether the given object is uniform or non-uniform. So if it is uniform, for a length L/3, the mass will be M/3. Okay. Suppose the length is L/5. Aishwarya, you tell how much mass will be present in a length of L/5.
M/5, sir.
M/5, 1/5 of the length, 1/5 of the mass. So the rod here is a uniform linear distribution of mass. Mass is spread on a line. Okay, we call it as linear mass distribution. And for a linear mass distribution, total length by total mass will be equal to small length by small mass. Okay, basically the idea is that mass is proportional to length in linear mass distribution. And total length by total mass or small length by small mass, we call this as linear mass density. One of you tell me from what you studied in your lower classes, what is density? How is density
Mass
of
by
a
volume,
substance?
sir.
Mass by volume, mass per unit volume. Okay, how much mass will be present in 1 unit volume is what is density. But we can define density per unit length also, per unit area also. Okay, you must have heard this term called population density. Can one of you tell me what is population density?
Like it's the number of people living in 1 kilometer radius.
Not 1 kilometer radius, per square kilometer. Okay, area. 1 kilometer radius also indicates an area only, the area of a circle of radius 1 kilometer. But population density, I think, is expressed as number of persons per square kilometer. Okay, so you can see that density can be expressed in different ways. Per square kilometer is an area, right? Like that, mass also can be spread over a volume. It can be spread over an area. It can be spread over a length. Like in case of a rod, the mass is said to be spread over a length. So here we define something called linear mass density. Denoted by the symbol lambda. Okay. So whenever mass is spread over a length, we can make use of this quantity called linear mass density. Lambda is nothing but mass per unit length. dm by dx you can write. Total mass by total length you can write. Or small mass by small length also you can write. That is what we mean by linear mass density. Okay. And if the rod is uniform, this term lambda, that is m by l or dm by dx, this will be same everywhere. So total mass by total length will be equal to small mass by small length, which is equal to lambda. Now for this rod, okay, why are we even talking about all this? Because we were stuck in the integration part. We had to express dm in terms of dx. We had to express mass of the element in terms of length of the element. So we are looking at a relation between the mass and the length. So we use linear mass density. Since the rod is uniform, we can write lambda, linear mass density, is total mass by total length, which is also equal to small mass or the element's mass by the element's length. So you can write dm, element's mass, is lambda into dx, where lambda is m by l, that we can substitute at the end. Okay, so mass is proportional to length. Proportionality constant is lambda. That's all. Now let us go back to the integral. We had to integrate x dm and divide it by integral dm. for the x-coordinate of center of mass. Therefore, x-coordinate of center of mass can be calculated as integral x dm divided by integral dm. Now we can express dm as lambda dx, where lambda is total mass by total length. That will substitute at the end. Now, since it's a uniform rod, lambda is same for every element, so you can put it outside the integral. Okay, anything which is constant or uniform can be kept outside the integral, and what will you be left with inside? X dx divided by denominator also dm can be, okay, you can keep it dm. Integral dm becomes the total mass. Or if you want, you can convert it to lambda dx. Keep lambda outside, integrate dx. It's up to you, but let's avoid that extra step. Dm is the element mass of one element. Integral dm becomes the summation of masses of all elements, which is the total mass of the rod. I have substituted it directly. Okay. And we want to find out the position of center of mass of this rod, where the mass extends from x equal to 0 to x equal to L. We want to cover the entire system, no? So the limits for integration will be from 0 to L. Okay, that's all. Now one of you tell me how much is integral x dx? Okay, you already told x square by 2. In this, we'll have to substitute the limits 0 to L. We'll do that. So we are left with lambda by m into, now if you substitute upper limit, it becomes L square by 2. Substitute lower limit 0, it becomes 0 by 2, that is 0. And we know lambda is m by L. Mass gets cancelled. You will be left with 1 by L into L square by 2, effectively becoming L by 2. That's the position of center of mass of this rod. Now, intuitively also you could have told that the center of mass of a rod will be its midpoint. But we proved it mathematically that center of mass of a rod, uniformly distributed rod, is its midpoint. Because the rod was extending from 0 to L. Center of mass turns out to be L by 2, which is the midpoint of the rod. Okay, like intuitively we could have told, but I want you to learn the procedure, how to mathematically derive the position of center of mass of continuous mass distribution. Okay, so we took a simple mass distribution, which is a uniform rod. Rod's total mass was m, total length was L. Okay, and what does uniform distribution mean? All the particles are similar. It's not like left side of the rod has 4 out of 5 parts of the mass and right side of the rod has only 1 out of 5 parts. No, it is equally distributed. Okay, now since there are infinite particles, you can't use the sigma formula, you'll have to use the integration formula. Integral r dm divided by integral dm. So if it's only the x coordinate that you want, integral x dm divided by integral dm. Only y coordinate, integral y dm divided by integral dm. So what is dm? Mass of one element. What is x? X coordinate of that element. So if you want to integrate them, you'll have to express the mass of the element in terms of dx, dm in terms of dx. Okay, that we did. To do that, what did we make use of? We made use of the fact that this is a linear mass distribution. Total mass by total length will be equal to small mass by small length. Based on that, we could express dm in terms of dx. And then integration gave us the answer as L by 2. Is it clear to all of you? Any doubts in this? Okay. We'll discuss one idea now, which will be useful for deriving center of mass of some other continuous mass distributions. Center of mass of a combination of systems. So consider something like this. Let's say there's one system having particles m1, m2, m3, so on up to, let's take 5 particles. And consider another system having maybe 3 more particles, m6. Okay, 4 we'll take. right? Now, one of you tell me, how will you express? Now, see, this is a collection of particles, finite number of particles whose masses we know. So you don't have to use the integration formula and all. Summation formula will be enough. So one of you tell me, how do you express position of center of mass of the first system? How do you express the position of center of mass of the first system? Saket, what's the formula, basic formula for position of center of mass?
Sir, M1 R1 by M1.
How can you take only one particle, M1 R1 by M1? Then M1 will get cancelled, you will be left with R1.
Oh, sorry, sir. Sigma of MIRL by.
So it is basically M1 R1 plus so on up to first system has 5 particles. So M5 R5 divided by total mass of the first system, M1 plus M2 so on up to M5. That's the position of center of mass of the first system. Next, the other system, if you consider second one, the position of its center of mass RCM2 is M6 R6 because the masses in that system start from 6. So on up to M9 R9 divided by the total mass of that system, which is M6 plus M7 so on up to M9. Okay. Now tell me, if you consider both systems together, Aishwarya, you tell, what is the position of center of mass of both systems combined? Like all 9 masses you take together, how will you express the center of mass position?
Sir, M1 R1 till M9 R9 divided by total mass.
So on up to M9 R9, correct. Divided by total mass. That is M1 plus M2 so on up to M9. Okay. Now in the numerator, that is M1 R1 so on up to M9 R9, you can write it like this: M1 R1 plus so on up to M5 R5 plus M6 R6 so on up to M9 R9. Okay, numerator is the summation of M into R of all the terms. I'm splitting it into 2 separate brackets. Divided by denominator also, M1 till M6 M5 I'll take in one bracket, and M6 till M9 I'll take in another bracket. Okay, why am I doing this? Now you observe this first term, M1 R1, okay, the first bracket, so on up to M5 R5. We can see that here also. Okay, and what can this be written as? This can be written as RCM1, that is the position of center of mass of the first system, multiplied with the total mass of the first system. We can write it like this. Okay. So what I'll do is this, whatever I have marked in square blue box, okay, not square, rectangular blue box, I can write this as RCM1 multiplied with total mass of the first system. For total mass, I'm using capital M. Okay. And then this term, the second term, or the second bracket that you see here, can be written as RCM2, position of center of mass of the second system, multiplied with total mass of the second system. And in the denominator also, this part is total mass of the first system, and this part is total mass of the second system. So effectively, what does all this change into? You get effective position of center of mass of the combination of two systems as mass of the first system into position of center of mass of the first system plus mass of the second system into position of center of mass of the second system divided by mass of first system plus mass of second system. Now observe this formula. This is like position of center of mass of two particles, m1r1 plus m2r2 by m1 plus m2. It's like position of center of mass of two particles. But in this derivation, this is actually the position of center of mass of two systems. Okay, a combination of two systems. So what this shows is that if you want to find out the position of center of mass of a combination of two systems like this, first system having a mass m1, second system having a total mass m2, what you can do is the entire first system can be treated as a single particle placed at its center of mass. Because the final formula we got is like that only. No, this is like the formula for center of mass of two particles. But it's actually the center of mass of two systems. So what it means is you can treat the system as a particle. But where should the particle be placed? At the position of center of mass of that system. So you can assume all m1 to be present here at this point. Similarly, you can treat the entire second system m2 as a single particle. Where should it be present? At the center of mass of the second system here. And effectively what you are now doing is just finding out the position of center of mass of this point and this point, this particle and this particle. Okay. So in this derivation, we see that center of mass of a system kind of represents the entire system in terms of position. Just a moment, let me adjust this. Okay. So if there's a combination of multiple systems, we proved this for two systems, but there could be any number of systems. So suppose there's a combination of systems like this, and you want to find out where is the center of mass of this combination. Treat each system simply as a particle placed at its own center of mass, and then use the particle formula. You will get the position of the overall center of mass. That's the idea. Why do we need this? Because it's not practically possible to keep integrating every time to get the position of center of mass of continuous mass distribution. Now, in this derivation, in the first derivation that we took today, we found that center of mass of a rod lies at its midpoint if the rod is uniform. Now, if you are given multiple rods in a question and asked where is the center of mass, you don't have to integrate for each rod. Okay, you will treat those multiple rods as a combination of single rods. And for each single rod, you know where is the center of mass. Then you treat them as a collection of particles and find out. Okay, we'll solve one problem, you'll understand. So the idea is that if you are given a combination of systems whose center of mass you know, individual system center of mass you know, you want to find out the combination center of mass, then each system is to be treated as a single particle placed at its own center of mass. So all the mass of the first system at the center of the first system, all the mass of the second system at the center of mass of the second system. Then treat it as a collection of particles and find out the effective center of mass. Okay. Let's use this idea. And this idea is very, very important. You'll understand. Assume these are the coordinate axis, and let's say there's one rod along the y-axis, or instead of saying one rod, I think I can just call it an L-shaped object. Okay, consider an L-shaped object like this. One part of the L along the y-axis, one part of the L along the x-axis. Okay. Assume the mass distribution is uniform. Means individual particles have the same mass. Okay, all particles are identical. And let's say the coordinates are given to you. Assume the length on this side is, okay, 2L by 3, or let's take it 2L just for convenience. This side length is 2L and this length is L. Okay, those are the dimensions of the L-shaped object. You have to find out where is the center of mass of this object. Okay. Locate the center of mass of this object. Okay. Now, if you want to integrate and all, it's going to be lengthy. One of you tell me, how are you going to consider this L-shaped object to find out the center of mass? What are you going to consider it as? Listen, is this a collection of separate particles or is it a continuous mass distribution?
Continuous mass distribution.
It's a continuous mass distribution. To find out the position of center of mass of a continuous mass distribution, you should either integrate or treat the continuous mass distribution as a collection of smaller systems whose center of mass you already know. Okay. So these are the only two ways. You should either integrate or treat it as a collection of systems whose center of mass you already know. Can this L-shaped object be treated as a collection of systems? And if yes, what is that system?
Sir, as two different rods.
You just treat it as two different rods. Correct. So the rod of length 2L is one system. The rod of length L is the other system. Okay. Now, you know where is the center of mass of a rod. For the part which has length 2L, the center of mass is here. You can call it as R1. And for the part which has length L, the center of mass is here. You can call it as R2. You can write their coordinates, X coordinate, Y coordinate. It's not very difficult. Okay. Then use what we just derived. What did we derive? If you want to find out the center of mass of a combination of systems, treat each system as a single particle placed at its own center of mass. So this system of two rods changes into a system of two particles. That's all. So you will have to consider it like this. Okay, I think it will be better if I place them side by side. Fine. One second. So two rods will be replaced with two particles. So you can remove this L-shaped object now. These two are identical. Okay. Try this, all of you. Find out the position of the center of mass. I got one answer as L by 6 I cap to L by 3 J cap. We'll see. Another as L by 4 and L by 2. Okay. See, what we have done is we have considered the two rods as two particles because we know where the center of mass of a rod lies. So the entire first rod of length 2L was replaced by a single particle. The entire second rod of length L was replaced by a single particle. Now all you are left with is like what you have to do is position of center of mass of this combination is simply mass of the first rod multiplied with position of center of mass of the first rod plus mass of second rod multiplied with position of center of mass of the second rod divided by the sum of their masses. Now their masses are not given to you. Then what to do? Okay, I think I told you in the last class also, to find out position of center of mass, you don't need to know their actual masses. All you need is the ratio of masses. Because last class we discussed, if there are two particles having masses m1, m2, then center of mass divides the line joining them in the ratio m2 is to m1. So all you need is the ratio of masses. Okay. Rishi, tell me, what do you think is the ratio of masses of these rods?
So 2:1.
2:1. How did you say that?
Sir, because one of their length,
Because the
one of
lengths
the
are in
length,
that ratio. Correct, correct. Because the lengths are in that ratio. Fine. We know it is a uniformly distributed L-shaped object. So one part has twice the length as the other. Then the mass also will be twice that of the other. Then the masses you take should be 2m here and m here. Okay. You can call it 2x, x, 2 kg, 1 kg. Just the ratio is what you need. You can take it as 6 kg and 3 kg also. Okay. Doesn't matter. Okay. And what is the position vector of the first rod center of mass? 0, L. So it's like 0 I cap plus L j cap. I'll directly write it as L j cap. That is the position vector of the first rod center of mass. Second rod center of mass. Saket, can you tell this position? Okay, Aishwarya, position of center of mass of that second rod, horizontal part.
Sir, L by 2, 0.
X coordinate is L by 2, Y coordinate is 0. So it becomes L by 2 I cap. That's all. We know the masses, we know the positions, we can find out the position of center of mass. Therefore, this becomes mass of the first part is 2m. Position vector of the first part is L j cap. Mass of the second part is m. Its position vector is L by 2 I cap divided by total mass of the system becomes 2m plus m. I'll directly write it as 3m. And this is why I said exact mass doesn't matter. It's only the ratio that matters. Because m will be common in the numerator and denominator, it will get cancelled. That's all. There you have the answer. If you write the I cap first, it becomes L by 6 I cap. And the j cap part will be 2L by 3 j cap. Aishwarya, did you understand your mistake?
Yes.
Okay. So the given L-shaped object is considered as a combination of two rods. Why are we considering it as a combination of two rods? Because we know where a rod's center of mass lies. Okay. So we are simplifying the problem. If you treat it as two rods, it's effectively a collection of two particles. Each rod is replaced by a single particle placed at its own center of mass. But the only thing you need to be careful about is how much mass you assign to them. And the mass you assign should be proportional to the length. So 2m on one side and m on the other side. Okay. Fine. So for a uniformly distributed rod, we know the center of mass is midpoint. We have derived that mathematically. Now consider a rod whose mass distribution changes from point to point. Or, okay, let's not change it from point to point, but just a moment. Fine, we don't need any of this. Let's say a rod lies along the x-axis. The left half of the rod, maybe it's made of denser particles or heavier particles. So the left half of the rod, let's say, has a mass of 2m by 3, and the right half of the rod has only a mass of m by 3. So total mass is m. Left half is uniform 2m by 3, right half is uniform m by 3. That is how the mass is distributed now. Okay. What I want you to find out is, let's say total length is L. So exactly at L by 2, the material changes. Left half is made of maybe a heavier material, so its mass is 2m by 3. Right half is made of a lighter material, so mass is m by 3. Calculate the distance of center of mass from the left end of the composite rod. Try this, all of you. Composite rod means rod made of different materials. Okay, left half is made of one material, right half another material. So I'm calling it as a composite rod. So I'll tell you how to begin such questions. You are asked to find out distance from the left end. So what you can do is you can assume the left end is x equal to 0. Then the first rod extends from 0 to L by 2, and the second rod extends from L by 2 to L. And you get the position of center of mass. Okay, see, obviously the left half is heavier, so center of mass will be in favor of the left half. It may be somewhere here. Once you get the position of center of mass, that itself becomes the distance from the left end. So you begin like this. You assume left end as the origin. Try. Okay, Rishi, how are you trying to solve?
Sir, when I'm taking the vector of the 2m by 3 part, should I make it minus I, or because the midpoint is at L by 2, right? Or will it just be,
Minus or plus depends on where the origin is.
oh, then it'll be plus only.
So tell me, so you are using the idea that it's a combination of two rods, right?
Yes, sir.
Huh. What is the position of center of the first rod? What are the coordinates of that point? Okay. Saket, where is the center of mass of the left half of the rod?
Sir, 2m by 3 by L by 2, sir.
What has mass got to do with that? See, okay, I'm telling this to all of you. From here to here is the left half of the rod. Left half is uniform. The entire rod is not uniform, but only the left half is uniform. It's made of heavier particles. Its center of mass will be its midpoint. No, I'm asking you, what are the coordinates of this midpoint? Why will it depend on mass? Aishwarya, coordinates of the midpoint of that left half of the rod.
Sir, L by 4.
L by 4, that's all. The left half extends from 0 to L by 2, then the midpoint will be L by 4 only, no? Okay. Yusuf, tell me, what is the x coordinate of the midpoint of the right half of the rod? Right half extends from L by 2 to L. What is the mid value? Anyone?
Real was
3L by 4. Okay. 3/4. Okay. L by 2 is 0.5. L is like 1. 0.5 and 1. The mid value is 0.75, which is 3/4. Okay. So we will treat this composite rod as a combination of two particles. That's all. One particle 2m by 3 present at this position. Another particle m by 3 present at this position. Simple. Therefore, the x-coordinate of center of mass of this composite rod becomes 2m by 3 m1 x1 plus m2 x2 divided by m1 plus m2. m1 plus m2 is the total mass. M is common in the numerator and denominator, gets cancelled. You will be left with 2L by 12 plus 3L by 12. The answer is 5L by 12. And 5L by 12 is less than L by 2. 6L by 12 is L by 2. 5L by 2 is less than L by 2. And that is what I was saying. The center of mass favors the heavier side. It's somewhere here actually. The balancing point. Anyway, we have not talked about this balancing point idea yet. But center of mass, that's actually called center of gravity, which is same as center of mass in many cases. Okay. So we are again using the same idea that a combination of systems can be treated as a collection of particles. So this composite rod is being treated as two separate smaller rods, and each smaller rod was replaced by a single particle at its corresponding center of mass. That's all. And we found out the overall center of mass of this system. Fine. We'll stop it here for today. Just a moment.